All right, hello. Thank you all for coming to this last talk of this conference, as far as I understand it. I'm just gonna get right into it. So I spent the whole day on airplanes today, and I was thinking as I was sitting in this United Basic Economy, I was thinking, how do we actually tell the difference between real flight attendants and people who want to dress up as flight attendants? There's not like a flight attendant authority who says, hey, you're not the real flight attendant, don't tell me what to do, etc. And as silly as that is, it's kind of a telling little motivation for this whole talk, as you'll see. Anyway, hello.
How do we know you're Ilya?
You don't. My name tag says it's Ilya. They didn't check my ID. Basically, when we communicate with software, when we interact with software, we don't really have a whole lot of guarantees that we're talking to the thing we think we're talking to. Sure, you can SSH into a server and it'll tell you what its fingerprint is, but what does that really mean? It means that there's some authority that tells you something about the system you're connecting to, be it a piece of a secret data that is on the system that you trust not to be on any other system, or perhaps some other piece of software that measures the thing you're connecting to and gives you its hash, or something else. But it's very rare that these authorities go all the way down to something we inherently trust. They just sort of float on this layer of poorly understood low-level stuff. Basically, without this authority, we don't really know what's going on at all. We connect to a system and it speaks the language and it looks like the thing we're supposed to be talking to, and we just sort of say, okay. For example, in this silly diagram, I trust a piece of software called Steve, and I connect to it, and I ask you, hey, are you Steve? And it says, sure, okay, yeah, I'm Steve. And you go, all right, and then you proceed to do your trusted stuff, but you don't really gain any guarantees from doing so. So in this talk, we're going to construct a small but very principled example of such an authority that would be able to convince you that it is indeed Steve. So the specific thing I'd like to do is I'd like to trust some hardware, because we already do that to do normal computation every day, and I'd like to have pre-existing trust in some piece of binary software. And I'd like to go through a trusted boot process, after which point the system will be able to tell me, hi, I booted this specific thing, and I can prove it to you, and you can trust this fact, given some threat model. Details of this, of course, are important, and the devil's in the details, so we're going to be a little scholarly about this and consider all the different things that a system does and consists of in order to make an actual threat model against which we'll set this discussion. So the system consists of hardware, and it has some root of trust software built into it, and of course it loads some binary, like for example an operating system or something like that, which in turn interacts with users, some of which log in, and also this machine exists in physical space in a room somewhere where sketchy individuals can walk up to it and do things to it. We're going to have to deal with all of these parties, and we're going to have to come up with a story for whether or not they're trusted, just how trusted are they, and what we're going to do about their existence. In this talk, we're going to take a fairly clear-cut approach. We're going to trust hardware unconditionally. We're going to have pre-existing trust in the software we want to load, which is also unconditional, although we've heard some talks throughout the day about using formal methods and really rigorous design strategies and things like that to garner some of this unconditional trust in binaries. We will also not engage with this problem of what to do with physical access adversaries, because once an adversary gets their hands on your system, it's really hard to convince them to do just the attacks you defended against. So, and then the rest of it, we kind of threat model out and say that the software that gets loaded by this trusted boot protocol, which will follow, will be trusted to handle anonymous users, authenticated users, and will also trust pieces of itself not to do bad things. Specifically, we're gonna trust the manufacturer to have a cryptographic identity that they handle responsibly. We're also going to trust the manufacturer to construct the hardware in such a way that it's trustworthy. It doesn't have any backdoors. They don't sell things that are not actually secure on the gray market, but still tell people that they're secure, and so on. We're also going to have pre-existing trust in this software image we'd like to load, and we're going to assume that the software image will be able to maintain its own integrity, and it'll be able to maintain privacy of a piece of secret data it is given. This secret data will be used for attestation, as I will show you soon. The adversary will be able to load arbitrary other software on this hardware platform, and it'll try to convince you, the remote user, trivially trusted, that the software that was loaded is in fact something else, something you expected, something that you trusted, whereas it is in fact not. We're going to threat model out the concept of denial of service, because if you're using a remote system, or if some piece of software runs on your system it is very difficult to guarantee availability of the system. For example, if you're computing on some Amazon Cloud thing, an Amazon Cloud operator person can literally unplug this machine for you, and there's not much you can do about it. So we're going to not discuss availability as part of this talk, which means that the party booting your machine could always corrupt the boot image and deny you any useful service. We're going to tolerate that. So I'm going to go through a step-by-step sequence of all the things that you need to get right as the altruistic manufacturer who wants to provide secure boot to the users of your chips. First of all, you need to be a trustworthy certificate authority. You need to generate a key pair. You need to guard the secret half of this key pair very well because it'll underpin the security of the entire ecosystem that is your secure computation platform. So if you build 1 million chips and each of them is trusted to guard 1 million, so each of them is trusted to guard about $1,000 worth of security, and then you get 1,000 times $1 million worth of value in this one key. So you're going to put a lot of armed guards around this key and make sure it never leaves a trusted facility, and only very, very specific access to it is permitted. We're going to build an entire key hierarchy starting from this point, which I will demonstrate in the graph to the right. So in addition to being a trusted certificate authority, the manufacturer is also responsible for building secure hardware. And in this case, I'm not going to tell you about the specific features the secure hardware needs to have in order to do trusted execution, because while that would be interesting, it's not really a part of this talk. We're going to assume some fairly bare minimum things from this hardware. We're going to assume that the manufacturer endows the hardware they build with a cryptographic key pair, and they're able to endorse the public half of the keys. We assume that the hardware they build is able to protect the privacy of that key, of the secret key. So if they sold you a chip with a public key, the secret key will never leave that chip and nobody will be able to clone it within a reasonable threat model. We're also going to assume that this chip gives you first instruction integrity, meaning that it'll boot from a trusted ROM that contains some program that the manufacturer provided. I believe that's it in terms of trust placed in the devices. We're not going to really argue for complicated features like enclaves or like the specific existence of PMP or things like that. All we really care about for the purpose of trusted boot is the presence of these keys, the safety and the privacy of the secret key, and the integrity of early execution. We won't even use the privilege modes of RISC-V. We really don't care about those until multiple mutually mistrusting pieces of software coexist on your platform, whereas during secure boot, only the one trusted piece of code in your boot RAM will run for a little while. After building these chips, the manufacturer needs to endorse them. It needs to read out the public key from the chips. Perhaps it already knows them because it wrote them in there, or perhaps they originate inside the chip through some sort of a manufacturing variation process like a puff. But either way, the manufacturer needs to read out the public key of every chip that they are willing to endorse as secure, and they need to sign it with their secret key and publish the certificate. This certificate will connect trust in the manufacturer's public key with trust in the chip's public key and endorse this chip as the real deal chip that was built by this trusted manufacturer that is capable of secure boot and not a sketchy emulator that some sketchy individual, published on GitHub and so on. You may notice that I'm filling out the key hierarchy on the right there. It's going to get a little deeper before we're done with this conversation, but so far it's been quite simple. So here's where we get into the detail of what happens once this chip is powered on and starts executing. We demand for this secure boot protocol to work first instruction integrity, meaning that when you turn this chip on or reset it, it begins executing instructions from its boot ROM, which a lot of RISC-V implementations that are open source conveniently have, and we're going to put a lot of secure things into that boot ROM. Specifically, the first thing it'll do is it'll load an untrusted boot image containing, hopefully, a piece of software with pre-existing trust in it. We can't assume this until after the secure boot is done. Essentially, we get an SD card full of bits, and we'll copy those bits as asked into DRAM, and we'll perform some cryptography on them in order to ascertain trust before we're done. All the while, we execute only within the root of trust in the boot ROM on chip. And we will take care not to delegate execution to a single user-provided instruction until after secure boot is over. Doing so would compromise the integrity of the whole operation. We do assume that the binary image we're booting has some structure. Specifically, we assume that there's a field in it that describes how big the thing is. It's very useful. And we also have some reserved space where keys will go. as secure boot fills out these data structures. After boot, there will be predetermined places in memory where various keys, certificates, hashes, and so on will end up, such that the post-boot environment can use them to prove its authenticity. After initializing memory, the boot ROM needs to do some other things. Specifically, it needs to compute a cryptographic measurement of the post-boot environment that it's hoping to bootstrap security for. Well, to do that, we conveniently have a size and a predetermined location where this post-boot environment binary starts. We simply take a cryptographic hash of that entire area, and we store the resulting field, the hash of S, in a predetermined location. It's quite simple so far. To do this, we rely on a cryptographic library, a portable implementation of SHA-3 that we scoured through GitHub to find, and it seems to be solid. As you'll see, most steps of this boot protocol will look kind of like this, where we take two existing fields and we'll combine them in a straightforward way and put the result somewhere else. I guess I have a note in pink at the bottom of the slide here. This didn't fit into the main presentation, but because the trusted boot protocol does quite a bit of cryptography here and there, some of the platforms we looked at had problems with being able to fit the entire trusted boot executable into the boot ROM itself, because some of the platforms we looked at only had a page of boot ROM available. And we noticed that all we really needed in order to have a trustworthy root of trust was a piece of code that is able to hash memory and a comparison against a constant. So after loading the entire DRAM image, the pre-boot image, we're able to authenticate the real bootloader that is trusted in DRAM against a constant by initializing DRAM, hashing the area of DRAM that is expected to contain the root of trust bootloader, and comparing that against the constant. It's a fairly simple realization, but it allowed us to have a tiny, tiny piece of hardware with the root of trust in it and ship the actual slightly more complicated boot ROM as a piece of the boot image on an SD card, for example. So after computing the hash, we need to endow this post-boot environment with keys. In order to do that, we're going to be using the ED 25519 elliptic curve crypto system because we like it. It's very permissive, it's unencumbered by patents, and it is quite fast. So we're going to use their KDF function to generate from a hash of the device's secret key and the measurement of the S environment, a pair of keys that is unique to this specific device and this specific post-boot environment. This is very important. If an adversary attempts to load a different post-boot environment, changing even a single instruction in S, this will change the value in H of S significantly, and it will change the keys that this KDF outputs, which means that an adversary can boot arbitrarily malicious code, but that malicious code will not have the same keys, and therefore will not automatically compromise the security of an honest post-boot environment. This model is not always appropriate for systems that could, for example, injure somebody if they do untrusted things. This is only really appropriate for a system that we'd like to attest the authenticity of after it runs, but it's a good starting point because we can use this to gatekeep systems and prevent them from booting unauthorized code at a later time. I also haven't mentioned in quite enough detail yet where this secret key of the device, SKD, comes from. That is quite intentional. It's a bit of an open area of research. In the Sanctum project that you heard mentioned earlier, we advocate for an existence of a PUF, a physical unclonable function that outputs some entropy from which we generate a pair of keys. But that's quite complicated, and we realize that's not always the right thing to do. So we assume that the hardware platform provides a function by which this secret key D can be exposed. Perhaps it's preloaded into some non-volatile memory by a manufacturer. But crucially, it needs to be able to be masked at a later time such that the post-boot environment doesn't have access to it. I will underline this point again when it becomes relevant. We derive keys for S. And after deriving keys from S, we need to endorse the keys for S, connecting the public key of S and its hash into a chain of certificates that goes all the way back to the manufacturer. This is quite straightforward. We essentially just sign the hash of HS and public key of S with the device's secret key. At this point, the device's secret key is no longer necessary until the next reboot. In fact, it's quite dangerous to have it lying around, so we're going to go ahead and clean up in the next step. So if you've been paying attention to how things are laid out in memory, I haven't been diligent about telling you where things go exactly, but all of the things that are volatile and sensitive essentially went onto a page of stack that's been pre-allocated as part of this boot image. And very conveniently, we can just erase that page of stack, blowing away all of the private information in the system that is architectural. We still need to erase registers. We still need to clear the caches or anything else that's threat modeled as relevant in our secure boot protocol. But essentially, erasing the actual keys from memory is quite simple because they're all on the stack. Also, as part of this cleanup phase, we crucially have to hide the secret key of the device. If we don't do this, then the post-boot environment can just emulate a secure boot protocol, deriving a brand new set of certificates using SKD for a completely fictitious binary that doesn't necessarily get loaded and produce arbitrary proofs. We can't let that happen, so we assume that the hardware platform provides a second function dealing with the device key, and that is the masking or hiding function. So one function to retrieve the secret key of the device available after reset, and one to make it no longer retrievable until the next reset. If you're curious about a bunch of different implementations of this, you can read the secure boot paper linked in this PDF, or if you can Google my name. And here's where things get a little interesting. So we've booted. Now Linux, for example, can run, and Linux will have access to all these fields, and you can log into it, and Linux will happily tell you that it has all these public keys, but you really have no reason to trust any of this unless the system can produce a proof that you can link all the way back to a root of trust, that being the device manufactured by a trusted manufacturer. So in this silly example, basically one computer can ask the other, hey, are you Steve? And it says, yes, I can give you a proof that I'm Steve and I'm running on this hardware that's manufactured by this manufacturer you trust. And the data, the graph relating all the pieces of data cryptographically is given on the left, and there's a lot going on, but crucially, basically what's happening here is we're hashing a lot of fields together, and we're signing them with the secret key given to the post-boot environment. SKS, the post-boot environment's secret key, is used to sign all of the information about the system that is relevant. What is the hash of this S? What is its public key? What is the device's public key? What is the manufacturer's public key? Did the manufacturer's public key include a certificate? If so, what is it, etc. So all of this creates a signature over a data structure that together is an attestation. This attestation is essentially a proof saying, hey, I have this private key S, and it corresponds to a chain of certificates that you should trust because you trust the manufacturer. The verifier validates all the relevant fields in this proof. It checks to make sure that the public key of the manufacturer in fact matches what they trust. It checks to make sure that the public key of the device is the one endorsed by the certificate given by the manufacturer to the device. Likewise, it checks to see whether or not the hash of the software matches some pre-approved constant of the trusted binary, and it makes sure that the certificate covering the post-boot environment matches the public key of the signer of the attestation. All in all, you get a proof saying that in response to the hey, are you Steve query, the computer you talk to is able to produce a signed data structure guaranteeing its access to S in response to this query. We're not quite done though, because this isn't actually sufficient to guarantee anything. This only guarantees that the system you're talking to has access to a system that has access to this secret key S. This is a pretty classic man-in-the-middle attack. So essentially, there could be a malicious proxy that just forwards all the requests for attestation to this unsuspecting, honest computer that did in fact perform secure boot in order to gain your trust and completely violate it after the fact. The solution to this is fairly straightforward if you've done any sort of cryptographic algorithms before, if you've done any sort of network security before, but in case you haven't, the thing we want to do here is key agreement. We want to agree on a shared key between the two endpoints that communicate, and we want to make sure to include the agreed upon key in the attestation. Conveniently, this elliptic curve crypto system we're using has a very robust key agreement primitive. It has a primitive by which it takes one party's public key and the other party's secret key and produces a secret that is the same as the inverse of basically the secret key of the other party and the public key of the other party fed through the same function. It's quite nice. Essentially, both the verifier and the party being verified can produce the same key as long as they're communicating with the parties they expect to be communicating with. To do this, the verifier has to generate a key pair. The verifier produces its own public and private key. It endows the attestation request with its public key. It expects the software being attested to derive a shared secret, and it expects this shared secret to be the same as its own. Now, the important thing comes next. This key has to be included in the attestation to make sure that it binds the party you're communicating with to the attestation itself. This makes sure that the attestation has not originated on some other computer. And then finally, you can produce a proof that a computer you're talking to has indeed loaded the correct software and has access to that software's secret key. So I hope that wasn't too confusing. I'm going to extend this a little bit in the next few slides to do some fairly straightforward but RISC-V relevant things, because the default configuration of a rocket ship has multiple cores, and at no point in this talk have I mentioned the word multicore, and there's some synchronization that needs to happen. It's not very complicated. There's a bit of a caveat. When you first boot the system, you can't trust the contents of memory. And if you can't trust the contents of memory, you cannot actually implement normal memory synchronization primitives like a barrier. So we've implemented a different barrier using interrupts, which is very, very similar to what the Berkeley bootloader does at boot. Essentially what we have is when the cores boot up, all of the cores ask the system whether or not they are core 0. If they're not core 0, they stop and they wait for an interrupt. If they are core 0, they do all the bootloader things that I just talked about, and then wake up all the other cores by sending interrupts to them. It is a very rudimentary barrier, and it works okay. Another thing that's relevant here is what to do if the software you want to boot has to be pre-approved. For example, if this is some weapons system or some medical device or something like that, it would be very unfortunate for arbitrary users to boot malicious code and then wait for an attestation not to succeed for some party to realize that this should never have happened. People can get injured. That would be bad. So two very simple ideas for a gatekeeping bootloader, which is very much in line with what you'd expect to see from a typical productized secure boot feature. Essentially, here the pre-boot environment, the root of trust encodes a specific hash of the software it expects to load, perhaps a list of specific softwares it's allowed to load, and it can make a binary decision whether or not to proceed with the bootloading process after it has computed the hash of S. This isn't very robust. This pre-whitelists all of the software the system will ever be allowed to run with secure boot guarantees, and it kind of goes in the way of this idea of patching and fixing that we like. So we'd like to delegate this to a certificate, and the way we do that is we expect the manufacturer to endorse a specific piece of software with its own certificate, such that when the system boots and the hash of S has been computed, a new piece of data comes in as part of the boot image, the certificate covering the hash of S signed by the manufacturer, and if the certificate is valid, then and only then can secure boot proceed. If not, again, we panic, basically meaning we go into an infinite loop until a reboot happens. Just to sort of give you an idea for what this looks like. We've implemented this in Portable C. We also used some libraries for cryptography, and I've given you an idea for how large all the components are. Okay, so by far the largest component of the secure boot protocol is the elliptic curve cryptography library. This does not actually include certificate verification code. This is just key generation and signing, but it's quite large. It's thousands of lines of code. The control flow for the secure boot, however, is tiny. It's about 200 lines of code. The AES library is small, at 400, and the SHA-3 implementation, we really like SHA-3 because it's tiny, is, as you can see, quite tiny. How does this compare to other bootloaders? Well, I'm not really trying to criticize existing work. I'm just trying to come up with a small example built on cryptographic principles that convinces you that what has been booted is in fact what it says it is. But existing bootloaders tend to be pretty feature-packed. They have file systems built into them. They do I/O, and as a result, they weigh in at thousands to millions of lines of code. I have opinions about that, but they are good products. Essentially, what we're trying to say is this is a good starting point if you'd like to build a really bare bones primitive to boot something on a fiddly processor without an existing deep infrastructure already available. And we hope that this will serve as a useful example. I should also point out that there are some things we've swept under the rug in this presentation. First of all, I haven't really talked about the trust in S to keep its secret key secret. This is a very difficult proposition. It motivates projects like Keystone and Sanctum and so on. Essentially, large software cannot effectively guarantee absolute privacy to valuable data today, as has been demonstrated by Spectre and the like. We're basically kicking the can down the road, and we say the software we do boot securely is expected to keep this key secret. A good place to start in the RISC-V ecosystem is PMP. It will give you some guarantees if you don't want to subscribe to an entire deep software ecosystem like Keystone or Sanctum. And we also haven't really discussed where the secret key of the device comes from other than my brief aside, but that too is an interesting area of research. I think for most projects it would be entirely sufficient for there to be non-volatile memory accessible via a narrow interface, but it would be exciting to generate keys from noise. Doing so would allow us to trust the manufacturer less, since the manufacturer would not have a copy of the key in your device. Thanks.